In this video, we will discuss Torricelli's law, named after the Italian physicist Evangelista Torricelli. This law is actually a special case of Bernoulli's equation, but was discovered earlier. In order to discuss Torricelli's law, let's look at this experimental setup. We have a container filled with some fluid up to a height uppercase h. At a different height, lowercase h, there is a hole in the container from which the fluid can flow out. The question is now, what's the velocity of the fluid that flows out? To find out, we can use Bernoulli's equation, which states that these three contributions to the pressure in a fluid are constant at every point in a fluid. So at the top, the static pressure is the atmospheric pressure. The dynamic pressure is negligible since if the container is big enough, the fluid surface will not move noticeably. And the gravitational part is determined by the height uppercase h. Whatever pressure this results in, it must be the same at the exit. The static pressure is again the atmospheric pressure, the dynamic pressure is determined via the exit velocity v, and the gravitational part is specified by the height lowercase h. Applying Bernoulli's equation means that these terms must be equal, and solving for the velocity v leads to this result, which is proportional to the square root of the height difference. Before we can realize why this might be interesting, let us also quickly look at another setup from classical mechanics. Suppose we let a ball drop from a height uppercase h and measure its velocity at the height lowercase h. Hence, its velocity at lowercase h is only due to converting potential energy to kinetic energy. This is a simple calculation using conservation of energy, which leads to a velocity that looks exactly like the velocity we got earlier. And that is Torricelli's law. The velocity of a fluid flowing out of a container is the same that an object would have if it would fall the same distance. And that's pretty much it for this video. Thanks for watching.